Hello there. You are welcome to class. As usual, I will advise us to subscribe to this channel so as to keep abreast of whatever lessons we post. So far in this course, we have been able to deal with topics like differential calculus and its applications. We have also been able to deal with some reviews of integral calculus. We went on to actually have some things on numerical integration, a way of integrating some functions that are not easily integratable using the conventional analytical methods. We played emphasis on the trapezium and the Simpson's rules. Today or next, we are going into another aspect of numerical integration, which is the applications of integration. There are many applications of integration depending on the field we are talking about. But in the case of this course, we are limiting ourselves to just about three. We'll discuss them, have some worked examples, and so be it. We go. Applications of integration. The first one we are dealing with is the average value of function. We use integration to determine the average value of a function. Suppose f of t is a function defined on this interval, a less than or equal to t less than or equal to b. That is, the range of t is between a and b. The area under such f of t, under that curve, because f of t will be a curve, could be a curve, could be a line, depending on the function being dealt with, is a integral of a to b f of t dt. Now let's consider a rectangle having the base a to b. That is, the breadth or the length of the rectangle is b minus a. Height is h. The area of such a rectangle need to be h multiplied by b minus a. Looking at this figure, this is a curve. This curve here is the f of t. This curve is the f of t. Then we have h and we have a to b. So meaning that the area under this curve is the integral value of f of t. The area under this curve which aligns with that rectangle, that is to say h into b minus a is equal to the integral from a to b of f of t dt. That is to say h is now integral of f of t from a to b all over b minus a gives us 1 over b minus a into integral of a to b of f of t dt. That is to say, h then is the average value of the function f of t across an interval a comma b. H that we just found is the average value of the function across an interval a comma b. That's one of the areas of applying integral calculus. Let's see an example. Find the average value of f of t equals t squared across these two functions, these two limits rather, a 1, 3 and b 2, 5. Look at it. The solution, average value from what we derived before, integral 1 to 3 of t squared dt over, that's b minus a, that is 3 minus 1. That gives us this value, 13 over 3. And for the other one, where I have 2, 5, we have this giving us 13. This is straightforward by just inserting the values into the formula for the average value of a function. Let's look at this note. It said if the interval of integration changes, the average value of a function will likely change, as you can see from here. So let's see the second example. You have to consider a sawtooth waveform in the next figure. Calculate the average value of the waveform over a complete period. Over a complete period. This is a sawtooth waveform. For those in electrical engineering, this should be something you are used to. This is a waveform. This is over a complete period. This is a complete period. It goes and comes back here. That's a complete period. Figure 2 is that waveform we have to work on. Solution is this. The first thing, because you are given only the waveform, you don't know the function. we first need to get the function, because without the function, we cannot actually do or find the average value of that function. So we have to find is the equation for the waveform is first obtained from 0 to t to 2. That means for this is v and this is t. So 0 to 2 is our period that we are selecting. Then from the straight line equation, v equals mt plus t equals mt plus c. Now when t equals to 0, v is 0. Now we need to say c becomes 0. When t is 2, v is 5. That gives us m to be 2.5. We want to get an equation using the straight line equation mx plus c. But here we have mt plus c because our x-axis here is t. So that we've gotten c and we've gotten 2.5. Therefore, v equals 2.5t is the equation of the waveform. V equals 2.5t is the equation of the waveform in figure 2. Now, I've gotten the equation. Our work is half done. The next is to get the average value of the function. V equals 2.5t. That gives us this. Using that our formula, it is now 0 to 2, 2.5t dt. That's 1 over 2, 2.5t squared, that is 2 from 2 to 0. We are looking at definite integral here. This gives us equals 2.5 v, 2.5 volt. Because this is, we are doing this v for volt and this is t for time. We are looking at this, it's a signal that gives this kind of waveform, and it's v against t. So let's say another example. An example, the current I of t for the periodic waveform in this figure 3, is I of t equals 20 exponential minus t between 0 and 10. Between the interval is 0 and 10, and period is 10 seconds. Period is given as 10 seconds. A, calculate the average value of current over a period, and then calculate the RMS value of current over a period. Okay, this is another area of application here is the RMS value. We have been dealing with average value. I just introduced the RMS value here so that we use it to get it from this same problem. Firstly, let's do the A. The average value, interval is 0 to 10 is considered because if here, we can just pick 0 to 10. What happens here, we happen here, we happen here. It's a periodic function. So there's a repeat of what happens at each period. So we taking just one period is sufficient to do our work. So IAV, that I average now, the average value of the current is 1 over t, 0 to t, I or I of t dt. That gives us this, slotting 20 exponential minus t dt from 0 to 10. 1 over period is 10. It goes to this. That gives us this particular answer. So that gives us 2 amperes. Substituting and solving gives us 2.0 amperes. Now the second one is IRMS. And I wrote here, the second application I'm talking about is the root mean square of a function. After talking about the average value, I thought root mean square. So this example is for the root mean square of a function. Root mean square of a function, or RMS, or effective value of a function. That is giving us this particular thing here, the square root of integral from t1 to t2, I of t squared dt all over t2 minus t1. We are given just for that particular problem we just solved for the average value here. So we have t, this, and then I of t is 20 exponential minus t. Solving that, using that same formula, will give us 200.0 here. And then the RMS itself will give us 200 over 10. Finding the square root of that gives us 4.472 amperes. 4.472 amperes. That is getting the IRMS, that's the RMS value of the current that particular waveform is representing. Now, example 4, now strictly on the RMS value. This second example on the RMS value of f of t equals a sine t across this interval 0, 2 pi. 0, 2 pi. That's the limit is from 0 to 2 pi. So this is what we have. Looking at that from that first example, the RMS current, RMS value of this f of t is, we give us this. Now you have to go down. This is what we did here. A squared sine squared t. Coming here, breaking it down. This trigonometry, break this down, gives us 1 over cos 2t over 2 if you remember your trigonometric functions, this gives us that when you now integrate this, we have sine 2t over 2. Slotting in your limits, 0 and 2 pi, gives us 0.707 amperes. Sorry, 0.707 ampere rather, for the RMS value of the. This is when RMS. In this particular example, we are assuming is a current value. That's why we are limiting it. We are going to unit as ampere. It can say for you to try. Calculate the RMS value of this function, f of t equals a sine omega t plus phi across this limit 0, 2 pi over omega. Calculate the RMS value of f of t equals a sine omega t plus phi across 0, 2 pi. That is that. Now, the third function, or the third application area for integral function, for integration, is the orthogonality of a function. Orthogonality of a function. Use test of orthogonality is another application area of integration. Two functions f of x and g of x are orthogonal over an integral a, b if the product of f of x and g of x integrated over the interval a and b with respect to x is equals to 0. That is to say, if you have an integral a to b of f of x multiplied by g of x, integrate with respect to dx, with respect to x, will give us 0. Example, you have to show that f of x equals x and g of x equals x minus 1 are orthogonal on 0, 3 over 2. On 0, 3 over 2. Solution is this. 0 to 3, from 0 to 3 over 2. Multiply x and x minus 1 dx. Integrate that. They give us this, s squared minus x. When you slot this in, when you integrate s squared minus x between 0 and 3 over 2, they give us 9 over 8 minus 9 over 8 equals 0. Hence, f of x and g of x are orthogonal over 0, 3 over 2. This is how to use the test of orthogonality to prove if two functions are orthogonal to each other. That's another important area of applying integration. Now I'm through with that. That's what I want. Application areas, I said limiting to just 3 for you to digest and understand well. These are a few exercises on applications of differential calculus. This is 1, this is 2. A curvilinear path carved out by a jetliner in space is given by 4x cubed minus x squared equals 25 minus 4xy. Find the equation of the tangent and that of the normal to the curve at 0, minus 2. Second question, the flow of charge through a cable is controlled by a switch and is given by Q of t equals 3t squared minus 44t minus 32, where Q is charge in coulombs and t is time in seconds. Determine the rate of change of the charge flowing with respect to time after 10 seconds. Then after how many seconds will the charge flowing through the cable be 0? Let's lay our hands on that. And the third one, determine the shortest distance between two curves, f of x and g of x, where f of x equals 2x plus 3 and g of x equals 5 over x. This is a hint for shortest distance calculations. We minimize p prime of x to be 0, where p of x equals g of x minus f of x. Let's lay our hands on these exercises. They will help us in understanding the application areas of both integration and differentiation. This is the fourth one. The volume of oil in the tank is controlled by a pump and is given by V of W equals 3W squared minus 44W minus 25, where V is volume in kiloliter and W is weeks. How many weeks will it take for the oil in the tank to be A, halfway, and B, empty? How many weeks will it take for the oil in the tank to be A, halfway, and B, empty. Let's try those. Thanks for watching and for listening to this lecture today. Don't forget to subscribe. Have a nice day. Thank you.